Good morning. Welcome to Krishna's class. In the last two lectures, we have looked at the geometry of linear functionals. And linear functionals do happen to be the main ingredients in the Hahn-Banach theorem. So now we are in a position to state the Hahn-Banach theorem and then look at the possible geometric interpretation of the statement of the theorem. So the theme of this lecture would be the geometry of the Hahn-Banach theorem. And of course, I put the statement here. And we also look at what it looks like possibly in R3, where you can actually visualize what exactly the Hahn-Banach theorem means. Okay, so let us start. First of all, let me just recall the interpretation of the linear function. Okay, so this is what we were talking about. So let x be a linear space. Over R or C. And generally, we were using the terminology K, okay, which is the in fact it's a field. So you can talk about linear spaces over a field, and we are actually interested in choosing the field as the real line or the field of real numbers or the field of complex numbers. Depending on that, we say X is a real linear space or a complex linear space. So X is a real linear space the associated field is when the associated field is R and a complex linear space when the associated field is C. So every time we will not be mentioning what the field is, we may use the word real space or the complex space. Okay. So now a linear function. So f k I can here change the whole thing into a linear space over K. Okay. Is said to be a linear form. If F is union. So it is essentially a map from the vector space to the associated field, which is linear. So the linearity property is, as usual, f of x plus y equal to fx plus fy, f of alpha x equal to alpha times of. So this is the condition, as we had been using it very frequently. So now you see that the first observation we have made is that the null space of is a subspace of X if f is not equal to 0, then NF, the null space of f, is a proper subspace of f. It's a proper subspace of X and is in fact a maximal proper by which you mean it's a subspace. Okay, it's a proper subspace, and it's a maximal proper subspace means what? See, it's a proper subspace means there exists an A belonging to X such that, in fact, there are several A's possible. A does not belong to and span of is equal to X. And for finite dimensional vector spaces, this would mean if the dimension of the space is n, then dimension of NF equal to n minus 1. If dimension of n minus 1, of course, the condition is that f is not equal to 0. If f is equal to 0, of course, it is a trivial situation, and you see that it is 0 for every f belonging to every element of the vector space. That is fx equal to 0 for every x belonging to x. And that's a trivial scenario. Okay, in that case, NF is equal to the whole of x. Okay, so whenever f is not equal to 0, then NF is a proper subspace of x and is in fact a maximal proper subspace of x. Maximal proper subspace means it's a proper subspace, but there is some non-zero element also, okay, some element in X which is not in the subspace, and with the property that the span of NF union A is equal to X. And in particular, if it's a finite dimensional vector space that you are considering, then dimension of f nf is equal to n minus 1. This is the outcome. Okay. So one thing that is clear, once you have a finite dimensional, a non-zero linear functional over a linear space, then the NF is a proper subspace, it's a maximal proper subspace. Okay, so what more you can obtain? So we can say that f a linear functional proper subspace. Okay, so the question that we had asked, in fact we have discussed this in detail. So given a maximal proper subspace of X, is it by here? Is it determined by a linear function on X? The answer is, in fact, we have seen that the answer is, but not unique. What? And what turns out is that every scalar multiple of f has the same null space as that of, therefore it is not unique. So what more you need? So we have shown that we can identify a unique linear function provided we fix the value of at some a belonging to x, but a does not belong to given this is what we have proved. Okay. Now clearly you know that if M is a proper maximal subspace, maximal proper subspace, if M is a proper maximal subspace of X, see, if X prime belonging to now define this is equivalent to setting f of a equal to 1. And of course, this would mean that f of x prime equal to 0. So this is a linear function. This is how you define a linear function. Okay. Then one can show that the following. X f equal to okay. So the relationship is as follows. Okay, given f, it uniquely fixes. Given an m, which is a proper maximal proper subspace of X, it fixes a linear functional f, but not uniquely, because it fixes some linear functional on f, and every other linear functional with this property is a scalar multiple. Okay, so that is why to fix that you set at the point A, after having chosen A, at the point A you fix a f of x equal to A. Now let us look at R2. Okay. Example. Look at R2. So this is R2. Now you know that the geometric interpretation of a proper subspace of R2, a maximal proper subspace of R2 is that R2 is M is a line passing through the origin. Maximal passing through the origin. Zeros. This is designated by M. Okay. Now choose such an A exists. Okay. So you choose an A. And fix equal to 1. Okay. Now what happens? You can show that for any b which is equal to a plus x prime belonging to M also has f of b equal to. Now what is this set? Okay. So the set of all b is equal to actually M plus, which is a line parallel to M through so it is essentially this one. This is the line parallel. Okay. Right? Now you will see that this enables us to write what are these? See, M plus A is a line parallel to the tricep. So M plus A is a line parallel to the line M. So M plus K consists of all lines parallel to the M, and this becomes the union of R2 is essentially the union of this class. Okay, and on each of these parallel lines, the way in which we have defined f takes the same value. Therefore, on this, f takes the value f is equal to 1. If you take Ka, suppose this is the point Ka, then you have a line passing through this, which is parallel to M. So, on this, f is equal to. Okay. Now, f is defined everywhere, and it is quite easy to prove that geometrically, verify that it's linear. So f takes the same value on each one of these lines parallel to it. So you see that the whole space is now stratified as the union of parallel lines. And on each line, on the line M corresponding to M, the value of f is 0. On all other, on each of the lines parallel to it, f takes a constant value. That is what the linear function is. Thus, what we have shown, corresponding to each linear function, there is a maximal proper subspace. Conversely, given a maximal proper subspace of X, there exists a uniquely determined linear functional if we fix the value of f at some vector which does not belong. Okay, so it is going to be tagged by that the vector and the value f takes at that point. Okay, so I think I have made everything. Now let us look at the now in R2. What is M? M is equal to the set of all x1, x2 such that equal to 0, a1, a2 are some real numbers. So this is the equation of the line passing through the origin. Okay. Therefore, and f of, so we define a2. Okay. Suppose such that equal to 1. There exists such a thing. Okay. Then f of K, where KB, K belongs to R. K is a real number or a complex number. So K belongs to, and X prime. Now this is the interpretation. So you see that the linear function is defined by f of a1 x1 plus f of a2 x2 or equal to some where E2. belong to M, and this is a unique breakup of a vector in. So in fact it is quite easy to see. This is what is happening. This is the line M. You take any x belonging to this. So this, and fix a B. You have got, this is the line, this is B, KB. This is the line KB. Now you see that you take any x belonging to that, then this can be resolved into a vector x prime plus some. This is the picture then, okay? Right? And this is exactly what it means. Okay? So on this, the line parallel to it get the same value k or f. Okay, so that defines the linear function. You can easily show that it's a linear function. Okay, so that's about, here we are not making any further structural assumption on the linear space, except that it is just a linear space. All these statements do hold. Now we are in a position to state Hahn. But before that, let me look at what are called normal spaces. So we say that X is a non-linear space. If X is a linear space, form defined for each vector. So we designate by, so we write norm of X so norm is a map from X to R, in fact R plus, okay, such that the following properties are valid. Equal to 0, 2, 3, norm of now and alpha belonging to K. K is either R or C. Now in this case, the field that you consider has to be either real or complex. Okay. So in that case, you can define a norm. So what is a norm? Norm is a map from X to R such that the map is non-negative. The map is 0 if and only if X equal to 0. That means the map of the 0 element is 0. The map of any element is 0 means that element itself is 0. And the map of alpha x is actually mod alpha into norm of x, and norm of x plus y, that is the map of x plus y is less than or equal to the map of x plus the map of. Such a map is what you call. So this is essentially the characteristic features of length, whatever. Okay. For a linear space. So this is essentially the length function. So the basic properties of the length are. Now you see, I want to make one remark here. See, there are two operations in the linear space. One, addition, and the other one is scalar multiplication. So here, you see, the first one says the nature of this is essentially a non-negative function, and then it is 0 everywhere. It is 0 if and only if x is the 0 vector. Elsewhere it is non-zero. So it is non-zero for all x not equal to 0. And then you see the property 2 and the property 3, you look. See, this concerns the linear space operations of x. Because in linear space operations, what are the operations? In x, there is addition and scalar multiplication. So that is basically, there are two operations, namely you can add vectors to get another vector. You can take a vector, take a scalar, take their product, and to get another vector of space. So we have to say that what this function does on the sum of two vectors. 2 says what norm does on a scalar vector. And 3 says how the norm of is related to the norm of the constituents. So the Hahn-Banach theorem is actually set not only on a linear space, but it's a normed linear space. So we are taking that specific condition. Okay. So Hahn-Banach theorem yet another thing that we will be talking about, linear functions on a normed linear. Now let f be a linear space. Then we can define, that f is we can define by x prime then x prime is an n-dimensional vector. Is a vector space. Okay, and you can also have x prime is also so now we assume x is a normal. space. Then we can define right as follows. This is also equally well valid on infinite dimensional spaces. So how do you define that? We define norm of f to be equal to divided by norm of x not equal to 0. Now this is the same as equal to 1. This could be even seen this. So this defines a norm. So X prime is also made a normed linear space. Okay. Now we are in a position. Okay, we will have a look at this in the case of the R2. So again, we return to the example. And over R. Now, there are several ways in which you can set a norm on R. So we will take one of them. So set any for instance, you can write see essentially norm x p you can write as where 1 infinity okay, and norm infinity or maximum of these are all the various norms that you can set. There are infinitely many ways in which you can set a norm. That is immaterial. So we choose one of them. Okay? We choose one of them. Right? And then you see that f of x is essentially equal to a1 x2 for x1 x2 belonging to R2 and a1 a2 R scalars are real numbers or complex or real numbers are real numbers. So we fix that. then f is fixed. Okay. So we will see what exactly is this. Supremum of equal to 1 or okay. So that you can compute. So if you are taking the function for some point x1, x2, it is equal to 1. So on plus a. Now suppose we set equal to 1. Okay. Okay. So this will turn out to be what is called the normal. So that when B1, B2 belongs to M, and for those, okay, this will be the normal, right? That is the definition. Okay. So that is no problem. So now it is a normal linear space. So let me now write what this uh, theorem stands for, statement of the theorem. So the theorem is, let linear space if f is a bounded on n, then f can be extended to a bounded linear functional f on x such that norm of okay, what is this? So we'll first find out what a bounded linear function is. So this is the statement of the theorem. F is a bounded linear function or a bounded linear space if norm of okay, right? Now let us see what this statement stands for. So let us look at the case. We will go to the general theorem later, but let us take x to be equal to let or R3. Let x so M is a two-dimensional subspace. Okay, so this is what you have. This is R2. Space. So these are the axes, coordinate axes. So this is your and the whole space is so M is actually equal to a copy of R. So isomorphic to R. Now what does it say? It says suppose there is a linear function. Suppose since we are working on finite dimension here, all linear functions are bounded linear functions. Okay, but if the moment you work on infinite dimensional spaces, that statement is not true. Okay. So this is the R2 subspace of that, and you have what you call a line passing through. So what is this line? This line all such that a1 x1 plus where of course a1 square plus, so that this is a non-trivial line passing through the origin. Okay. So it's a line essentially in R3 also, it's a line. Okay. Now what is this saying? You know that this line, since it passes through the origin, it determines a linear function provided you fix the value of small f at any point in R2 which does not lie on this. Okay. So f is defined. Some k. Is not immutable. Okay. So this is uniquely defined on that. So we can define it as this way. We set it's a bounded linear functional. Now what do you do? What the theorem says is that, see, you can consider all planes containing N. So this is any plane containing, consider any plane contains the line L. Okay. Now define the same A1 x1 plus A2 x2 plus A3 x3. Okay. Then this is some what do I call? This I have used already M. This is your M. This M is 1, 2. So I use the letter, say yes. Where A1 and A2 are the same as the one that is already chosen. So A1 and A2 are the same. As the definition of N. So what about this line? You see that S is S for different values of A3 are planes containing L. Not only that, by varying A3 over R all planes containing L. That means A is a parameter which determines, that is A3 determines such a plane. Okay. And when A3 equal to 0, we get In fact, x3 equal to 0 contains the given line. Or you choose A1, A2 as 0, 0 and A3 as 1. That contains, sorry, given line, okay, right. So by choosing A1, A2 equal to 0, you get the plane x3 equal to 0, that is the two-dimensional plane that contains the line. Now define this. Okay, right. So capital F can be defined in this way. This is defined as f of x1, x2, 0. Okay, that will give you the linear function, right? One can show that. Okay, so this needs a little bit of, it's not difficult. See. So that is the meaning of the Hahn-Banach theorem. If you try to analyze, is that if in M you have a linear function defined, you can extend this as a linear function in the larger space X. Okay, such that it's a non-preserving extension. That is the meaning of that, right? So here you have a linear function defined in R2 here is the x1, x2 space, and it determines a line, and once it determines a line, you can choose planes containing this. Okay, now any linear functional with S as any linear functional with S null space is an extension of okay. So what you do is you take this line, extend this to a proper subspace of R3, which is a line, which is a plane which contains this, and you know that it's a subspace of R3. Now define a linear functional which is with this as the null space, and that will be essentially the extension of the linear function small, and that is the content of the Hahn-Banach. That is the geometric content of the Hahn. Okay. Now our next task is to give a formal proof of the existence of such a. So once you work with R3, you will easily understand what is going on. Okay? The geometry will be self-explanatory. If you just spend some time on that, you get the hang of it. So once you understand it on R2 or R3, this is all the results in functional analysis. Once you try to decode it on R2 or R3, where you have a perfect visual perception, easily get it. You easily understand. So the best way to learn linear algebra and also functional analysis is to work on on try to see what it means on our. Thank you very much.